This is Honors Math 3, Unit 5, Objective 10. It's the last objective for Unit 5, and we are dealing with inverse functions. Okay, so start with the definition. Two functions, just call them f and g for sake of referring to them, are inverses of each other if, by the way, this terminology right here, IFF, in math, that means if and only if. Okay, do not use it in your English class. But in math, it means if and only if. And so it means if you have one, you have the other. So it's true going either direction. So two functions, f and g, are inverses of each other if and only if f of g of x, this is composition of functions, f of g of x is equal to x, and also if g of f of x is also equal to x. Okay, so now that's the definition. Now, if you have two inverse functions, here's a property about them. They are symmetric about the line y equals x. Now, any function will have a reflection, or in other words, an inverse across the line y equals x. However, the reflection is not always a function. And so that's part of what we are determining in these notes and on the assignment today. So let's take a look at these first three problems here. So problem number one, well, anyway, the directions here: sketch each function, identify its domain and range, sketch the inverse on the same coordinate axes, and identify its domain and range, and then determine whether the inverse is a function or not. Okay, so original function, f of x equals square root x plus 4 minus 1. Now, we've been doing that this unit, so hopefully we have a very good idea of how to sketch this sort of thing already, but you know, we want to get 3 points accurate each time. So you know, start with the vertex, -4, -1. Square root of 1 is very nice, so if we input a -3, and if we plug in a 0, we get square root of 4, which is 2 minus 1, which is 1. Okay, so -4, -1, and 3, 0, and 0, 1, and that's matching up to a half parabola that's opening up and to the right. Okay, and label it. Particularly, remember, anytime you sketch more than one graph on the same coordinate axes, make sure absolutely you must sketch what's going on. Okay, now how do we sketch an inverse, or how do we sketch a reflection on the line y equals x? Well, let's start by sketching the line y equals x. Of course, the line y equals x goes through the origin, has slope of 1. Okay, and so the way that you pick out points that are reflection across that line, you pick out points that are on the original graph, and you have them switch the x and the y. Okay, so for example, we have 3 points right here that we've clearly identified on the original function. We're going to switch the x and the y. So -4, -1 becomes -1, -4. Okay, and I'm also going to choose a different color so we can clearly see the difference between them two. So -1, -4. Okay, so right there. And -3, 0 becomes 0, -3. Okay, and there it is. And then 0, 1 becomes 1, 0. Okay, and now as long as we're doing a decent job sketching this, which I'm not doing a real great job sketching this other one. The two will look like they're mirror images across the line y equals x. Now, if they intersect, they should intersect right on the line of symmetry. Now, mine's very close. I'm off just a little bit. So, you know, these are sketches. Let's see, I need to label this one. Now this one is effectively our g of x, but there is notation for it. Well, let's just go ahead and call it g of x for right now. Okay, so g of x. Okay, let's see, what else are we supposed to be doing here? We're supposed to be doing the domain and range for the function. Okay, so the domain is obviously x greater than or equal to -4, and the range is y greater than or equal to -1. Okay, so there's information about f. Information about g here, my domain, x is greater than or equal to -1, and my range is y greater than or equal to -4. Okay, let's take a look at some things here. Let's see, what else are we supposed to do? We're supposed to determine whether the inverse is a function or not. Is there a quick way for us to figure out if something is a function or not? Yes, don't forget there is something called a vertical line test. If you pass a vertical line through the function going from left to right, or I guess it could go from right to left as well. But if you pass a vertical line, as long as the vertical line passes through the function one point at a time, then all the way through the function, then that function is, well, that graph is a function then. So the original f of x, that is very obviously a function because it would pass the vertical line test. And the function g of x is also a function because it passes the vertical line test as well. Okay, so I mean that's pretty much what was asked for us to do for this problem. Okay, did we notice anything else? I am noticing the domains and the ranges there's kind of some sort of similarity going on here. The domain of the original function is x greater than or equal to -4, and I see that the range for the inverse is y is greater than or equal to -4. And the range for the original function is y is greater than or equal to -1, and the domain for the inverse is x greater than or equal to -1. Wonder if there's something about that. By the way, we never did actually write down that, yes, the inverse of f is a function. Okay, moving on. Problem number 2. Okay, exponential function. It's been a while since we've done some of these, but let's go ahead and do that. Okay, so and again, you know, it's like we want some very specific points. Okay, so if I input a 0, 2 to the 0 plus 1 is 2. If I input a 1, 2 to the first plus 1. If I input a 2, 2 to the second plus 1. Okay, so and the fact that it's shifted up 1, don't forget that that means that there's actually a horizontal asymptote at elevation 1 out there to the left. Okay, so let's see, 0 to 1, 3, 2, 5, and we should know the basic shape of this graph. I'm not drawing it very well. And f, let's see, f, the domain is all reals, and the range is y is greater than or equal to 1. Okay, so there's that one. Okay, so let's do the inverse, although let's draw on the line y equals x. It's nice to draw on the line y equals x when you're doing inverse functions. So the inverse 0, 2 becomes 2, 0. 1, 3 becomes 3, 1. And 2, 5 becomes 5, 2. 5, 2. And remember our horizontal asymptote, y equals 1? Well, x equals 1 becomes a vertical asymptote. And so something like this, okay? And so we'll just go ahead and label it G. And G has domain, well, it looks like x is greater than or equal to 1. And the range, well, it goes from low to high. And it's covering all of those, so that sure looks like all reals. And if I do the vertical line test, then the function G, yes, G is a function. Okay, so that does everything that we're supposed to do. Although, let's take a look at the domains and the ranges again. And there's that same pattern going on here. The domain for the original became the range on the inverse, and the range on the original became the domain on the inverse. I wonder if that pattern happens all the time. Okay, moving on here. F of x equals x minus 3 quantity squared minus 2. So yes, it's a parabola. Yes, we should be able to do it very quickly. Let's start with the vertex. So 3, comma, negative 2. And a point to either side. So if I input a 4, that's 1 minus 2, that's negative 1. And if I do symmetry, then I've actually got 2 points out of that. So if I go 2 points to the side, so 5 minus 3 is 2 squared is 4, minus 2 is 2. So 3, negative 2, 3, negative 2, okay, 4, negative 1. But remember, parabolas are symmetric about their axis of symmetry. In other words, symmetric about that vertex. So if I go 1 point to either side, I'm going up 1. And 5, 2. Okay, so that was 2 points to the right. So if I go 2 points to the left on the other side, then it's also 1, comma 2 is also on there. Okay, so that should be a very good sketch then. Okay, so there's my function f. Okay, let's find some points on the inverse. And remember, all we have to do is switch the x's and y's. Let's see, okay. So 3, negative 2 becomes negative 2, 3. Okay, so there's negative 2, 3. 4, negative 1 becomes negative 1, 4. But remember, we had the symmetry thing going on, so we also had 2, negative 1. So negative 1, 2. And then we had 5, 2, which becomes 2, 5. And then because of the symmetry thing, when we also had 1, comma 2, so that becomes 2, comma 1. Okay, so we have here, and we have here. Okay, and so there's my function g. Yeah, you know, it's like those are symmetric about the line y equals x, and my points of intersection, if I was doing a very good, more accurate sketch, then sure looks like they would be intersecting on the line y equals x. let's see, my function f, the domain and the range. My domain is all reals, and my range are all the y's greater than or equal to -2. Okay, now for my function g, domain and range, okay, so my domain are all the x's greater than or equal to -2, and my range is all reals. So looking at the pattern that's been going on, yes, it looks like the domains and the ranges are just switching. Why is that pattern happening, by the way? Well, if you think about it, how are we getting the inverse? Aren't we switching the x's and y's? And isn't the domain all the x's and the range are all the y's? So if I'm switching each one of the ordered pairs, x and y, the domains and ranges are switching. Now, probably you guys already had all that figured out, but I just wanted to point it out just to make sure. And then is g a function? I think I mentioned that it was a function earlier, but if we look at it, g is obviously not a function. It would not pass a vertical line test. So no, the inverse g is not a function. Okay. So I wonder why that is. Why was the inverse a function the first two times, and why is the inverse not a function this time? I wonder if that's predictable. I would imagine, yes, that it's very predictable. Okay, so moving on. Property. For the inverse / reflection on y equals x to be a function, the original function must be 1-to-1 as opposed to many-to-1. Okay, what the heck does that mean? A 1-to-1 function means that for each x there is exactly one y, but there will not be any repeat y's, in other words. No repeat y's. So once a y value is used, it cannot be repeated. As opposed to many-to-1, and whether it's many-to-1, you can have many y's to each x for a many-to-1 function. Okay, so let's go back and look at that last one. So for example, the original function f, if I wrote out the other points, we had 3, -2, we also had 4, -1, but then we also had the 2, -1. And we had 5, 2, but we also had 1, 2. It was because of the symmetry thing going on. So there were many x's to that one y value, many-to-1 as opposed to 1-to-1. But 1-to-1 means effectively that there's going to be no repeat y values. Now, wouldn't it be nice if there was some sort of very quick way to test to see if it's 1-to-1 or many-to-1? And there is. We have a vertical line test to see if it's a function. There is a horizontal line test to test and see if something is a 1-to-1 or many-to-1. So on problem number 3, f, if you do a horizontal line, can you see how the horizontal line is passing through the function more than once? It intersects the function more than once as you go through. And if it happens even one time, it's a many-to-1 function. As opposed to number 2, if you do a horizontal line test, the original function is a one-to-one function. And the even number 1, the original function is a one-to-one function because passes the horizontal line test. Okay, so if the original function is one-to-one, then meaning that it passes the horizontal line test, then the inverse will be a function. Okay, so sketching, we now know how to find an inverse and to predict whether it's a function or not graphically, but we also need to be able to do it analytically. Okay, so analytically, to find an inverse function, we switch the x's and y's. That sounds familiar, and then solve for y. Okay, so we're going to do a couple of the problems where we're already familiar with them. Now, when you're doing these, I think it's a good idea to do a very quick sketch. That's why I have just a little bitty graph paper as we're doing something like this, just to kind of get it in your head what's going on. So y equals, we can just see 1, 2, 3, 4, -1, and we know it's doing something like that. And then at that point, you know, you're looking, you're going, oh yeah, that's going to be that's a one-to-one function. So we can see what's going on. Okay, so switch the x's and y's. F of x is a y, so x equals root y plus 4 minus 1. Solve for y. Okay, so I'm going to add 1. X plus 1 equals root y plus 4. And I'm going to square both sides, because that's what we do to get rid of the radical there. And so now what's nice about this is we just want to leave it as x plus 1 quantity squared, and the right hand side is y plus 4, and then subtract 4, so x plus 1 quantity squared minus 4 equals y. Okay, and now we know, because this f was one-to-one, that my inverse is going to be a one-to-one function. Excuse me, is going to be a function. The inverse is going to be a function. And so since I know it's going to be a function, and this one's name was f, there is notation. Instead of calling it g of x, we actually call it f, looks like f to the -1 power of x. So since the original was f, this is the notation for inverse function of f. It's read inverse function of f. It looks like a -1 exponent, but it's not actually an exponent, it's just notation. And okay, so that's f inverse is x plus 1 quantity squared minus 4. Now, isn't that a parabola? Yes. Vertex at -1, -4. Okay, and so, you know, it's like we know it's doing something like this. And so now we're just going, that's not the mirror image across the line y equals x. We only want half of that. Which half do we want? Now, if you have the graph going, it's pretty easy to see. You're going, I want the right side, because that would be the mirror image across the line y equals x. Okay. And so if you have the little sketch going, you say, okay, I want the right side. Well, how do I identify that I want the right side? Do a little comma, and then you say, okay, I want the right side of the vertex. The vertex is at -1, so I want x greater than or equal to -1. And yes, you need the comma, and yes, you need that x is greater than or equal to -1. So now that is the f inverse. Now, if you don't have the sketch going, you can be paying attention to the domain and the range of the original, because we know that the domain of this one is x is greater than or equal to -4, and the range is y is greater than or equal to -1. But we also know that the range on the original becomes the domain on the inverse. Okay, number 5, find the inverse function analytically for the function in problem number 3. Okay, so f of x equals x minus 3 quantity squared minus 2. Okay, so now we know that that one is a function, but it's not a one-to-one function. And we know that the inverse would not be a function if we did that. Okay, so what we can do, if they're saying find the inverse function, okay, we can restrict the domain so that it becomes a one-to-one function. Okay, now generally when you're restricting the domain, you still want to get all the elevations that are there. So effectively with this one, we want to do either the left half or the right half of the parabola. So, and if it doesn't tell you one way or the other, you can do it either way. Just for fun, let's say we're gonna do the left half. So we're going to put restrictions on it and say we're going to do x is less than or equal to 3. Okay, so now it's a one-to-one function. This is one-to-one. Okay, so switch the x's and y's. So x equals y minus 3 quantity squared minus 2, and solve for y. So x plus 2 equals y minus 3 quantity squared, and square root both sides. Okay, and the left side is root x plus 2, and the right hand side is absolute value of y minus 3. Now, we can avoid this step as long as you remember to do the plus or minus. And then we finish off by adding 3. Okay, so we've got y equals plus or minus root x plus 2 plus 3. Okay, now we don't get to do the plus or minus, because if we did the plus or minus, okay, let's see, negative 2, positive 3. If we did the plus or minus, we got the top half and the bottom half of the parabola. Now, if you have a sketch going, you could probably kind of pick out, and it's a very rude and crude sketch here, but you could probably pick out and you can say, I want the lower half. That's the one that I'm going to want, so that it's symmetric about the line y equals x. And you'd say, okay, I want the negative root thing. Or again, you could pay attention to domains and ranges, and so we know that this one, the domain on the original becomes the range down here, so x less than or equal to 3 becomes y less than or equal to 3, which less than or equal to tells us we're going to want to do the negative, okay? And so now we got, and we're writing inverse functions, so f to the negative 1, which inverse of f of x is negative root x plus 2 plus 3. Okay, I know the notes are going a little bit long, but it takes some time to get through all this, so this is the last problem. Given this function, which, and they're asking us to find f inverse of 0 and stuff like that, so it's going to be a one-to-one function. I'm not even going to take the time to do a quick sketch right now because the notes are going a little bit long. But let's find, we need to find f inverse, okay? So switch the x's and y's. So x equals y plus 2 over y minus 3. Okay, solve for y. So I'm going to cross multiply. So I get x, y minus 3x equals y plus 2. We need to get the y's together. So I'm going to move y to the left. X, y minus y equals, and I'm going to move the negative 3x to the right. And, okay, now, this is the part that sometimes stumps some students, but we got to be better than that. How are we going to get y by itself? There's a GCF of y. And so y equals 3x plus 2 all over x minus 1. In other words, f inverse of x is 3x plus 2 over x minus 1. So there's our function, f inverse. Okay, so if I want to do f inverse of 0, f inverse of 0, all I'm doing is plugging in a 0 to my function f. So I've got 3 times 0 plus 2 over 0 minus 1. which is 2 over negative 1, which is negative 2. Okay, f of f inverse of 2. So let's do the f inverse of 2 first. So f inverse of 2, so 3 times 2 plus 2 over 2 minus 1, which is, let's see, 6/8 over 1. Okay, so now I have to do f of 1. Okay, so f of 1, we'll go back to my original. So f of 1, that would be 1 plus 2 over 1 minus 3. And so I've got, did I do this correctly? 6 plus 2 is 8 over 1. Okay. Yeah, and it's not f of 1, is it? It's supposed to be f of 8. Sorry, let's try that again. Okay, so I'm doing f of 8. Okay, so f of 8, 8 plus 2 over 8 minus 3, which is 10 over 5, which is 2. And so we've got 2. Here we go. F of f inverse of 2 is 2. That's strange. We started with a 2, we ended with a 2. Okay, let's try the last one here, and we'll be done. Okay, so f of negative 5. Okay, so we're going to start with f this time. F of negative 5. So f of negative 5, I've got negative 5 plus 2 over negative 5 minus 3. Okay, so that's negative 3 over negative 8, which is positive 3/8. Okay, so now we need to do f inverse of 3/8. Okay, so f inverse of 3/8. And so let's see my function f inverse. Okay, so 3 times my input, 3 times my input, plus 2 all over my input minus 1. Okay, so that's 9/8 plus 2 over 3/8 minus 1. Let's see. If I multiply top and bottom by 8, I get 9 plus 16 over 3 minus 8, which is 25 over negative 5, which is negative 5. Negative 5. I said negative 5 and my hand didn't cooperate. Negative 5. Okay, so f inverse of f of negative 5. I started at negative 5. I ended at negative 5. Why is that happening? That's something you guys are going to have to think about.